All right, guys, today we're starting the second half of chapter 3. We're going to be talking about finding and using the slopes of lines. Okay, so I'm going to skip right to this slide right here to get started. The slope of a non-vertical line is the ratio of the vertical change, the rise, to the horizontal change, the run, between any 2 points on that line. Okay, if a line in the coordinate plane passes through points x1, y1, and x2, y2, then the slope of m is this. So I like this slide because we talk about rise over run, change in y over change in x, y2 minus y1, x2 minus x1, all meaning the same thing. Right? Here's your rise, your difference in the y's. Basically, how much did you go up compared to how much did you go over? And putting together that ratio. Right? Now, one thing I want to point out is this right here, a triangle, is the Greek letter delta. And occasionally, you'll see me use it. Actually, a little bit more than occasionally. I like using it. I like to, instead of saying change in y over change in x, I'll say delta y over delta x. Where you're really going to wind up seeing this is in like chem class, you guys. But I figured this is a nice way for me to almost connect those two ideas. So that might pop up as well. So different slopes mean different things, you guys. Positive versus negative. I mean, let's really think about what it means to be having a positive slope. If you have a positive slope, then as you go up, you go over. As you go up, you go over. Now, obviously, different slopes, right? We can be really steep or not as much so, and that will have a lot to do with what the ratio actually is, right? This is positive, and this is positive, but it's a different ratio. Let's think about what this really means, right? This is saying that you will go up 1 every time you go over 2, meaning you're moving more laterally, you're moving more to the side versus how much you're going up. Here, this is saying, yeah, I want you to go up 2 every time you go over 1. So what this is saying is, oh yeah, you're going to be moving up faster than you move over. All right, now let's think about a negative slope. The same thing applies. Maybe I have a really steep negative slope. And maybe it's less steep, but is still negative. All right. So 99% of the time, we'll be living in this world where these things occur. But I do want to talk about some special cases so that we're not surprised when we see them. The first special case that I want to talk about is the zero slope. Now here's the thing about the zero slope, you guys. The only way we get the zero slope is for our change in y over our change in x to equal 0. And the only way that that is possible is if you have 0 over the change in x. Because 0 divided by anything, no matter what the change in x is, will just be 0. So if you think about a change in y that's 0, that means your y never changes. So let's think about what that will look like on a coordinate plane. What it means is that you have some point, some xy, and some other point with a different x value, but the exact same y value. So the zero slope is always going to be a horizontal line. And like I said, 99% of the time we're going to live in a world where it's an actually calculable slope. But sometimes we'll get a zero slope, and I want us to remember what that means. These formulas are always going to be written as, y equals, I don't know, we'll call this 2. Right? Where basically there is no slope worth writing. We just write y equals 2 because that's what's consistent across the board here. It's just that the y value stays the same. So next is the undefined slope. Okay. So as you could guess, if we just went through the zero slope and said that it's horizontal, there'll be no surprise when I say the undefinable slope is vertical. So zero slope is horizontal, undefined slope is vertical. Let's think about why a vertical line has an undefinable slope. If I draw the situation and I draw a vertical line in here, let's think about what's changing from this point to this point. What's changing isn't the x. I'm never moving left or right. I'm just moving up or down. If I'm just moving up or down, then when I calculate the change in y over change in x, I might be constantly changing in my y, so I'll be able to calculate it, but my change in x is 0 because I never move left or right. I never go anywhere. And am I allowed to divide by 0 in mathematics? No. So we say that's undefinable. It's an undefinable slope. How do we write the equations for this stuff? Well, the only thing that's consistent is the x. So if this is x equals, I don't know, like -1, then you just write x equals -1. Because what all of these points will have in common, this point and this point and every single point in between and on and on and on, is that they'll be at the same x location. Their y's might change, but their x never does. So all you ever need to do this stuff, you guys, is just 2 points. So I have a quick example for us to do right here. I like to do stuff like this. I like to remind myself, okay, I'll call this x1, call this y1, I'll call this x2, and this y2. Now, here's the deal. If I wanted to flip-flop these and say that this is x1 and y1, I can. What I can't do is accidentally mix them up where I say, oh, this is x1 and this is y2. No, you just need to be consistent. So I'm going to do the difference of my y's, 12 minus 8, over the difference of my x's, 8 minus 5. That's 4 over 3, which cannot be simplified. If it can, I should simplify it, but this can't be. And that's the slope, and I'm done. All right, it is a pretty straightforward formula, which is good. So one thing that we need to add, the last thing that we're going to add for today's lesson is the slopes of parallel lines and the slopes of perpendicular lines. Slopes of parallel lines are always the same, right? And that's worth memorizing, but also let's think about it conceptually. If you're never going to collide with another line, then you need to be moving at the same rate. Because the second you start moving at a different rate, eventually you'll run into each other, right? With perpendicular lines, it says here that the two non-vertical lines are perpendicular if and only if the product of their slopes is -1. Really, the better way to think about this is opposite reciprocal. Opposite reciprocal, okay? When we break down what opposite reciprocal means, okay, opposite reciprocal. The opposite means we need to change the sign. Again, is that worth memorizing? Of course it is. But let's also look at the context of the problem. If I have the red line here, it's clearly a positive slope. Positive slope. There's no way that I could come in at 90 degrees unless I was a negative slope. There's no way, right? If I had another positive slope, right, I might be able to do something like this, right? Or like this. But it's only once I switch over to being a negative slope that I can actually come in at 90 degrees. Now let's think about what I mean when I say reciprocal. That means flipping the slope. If you consider that this red line almost looks like it has a slope of like 1/2, right? It's moving pretty slowly. This clearly is much more steep, right? Clearly. So we flip it over. So it's important to remember and like memorize this, that if you have a slope 1/2, the opposite reciprocal will be -2/1. If you had -2/1, the opposite reciprocal will be 1/2. It's good to memorize that, but let's also think conceptually that it makes sense that for me to come in at 90 degrees, I must be the opposite sign at the very least. And then remembering the reciprocal as well. One last thing I want to talk about, you guys, is how we can use this information about perpendicular lines to solve problems. In general, in this chapter, and in geometry always, I encourage you very seriously to please draw the situation that the problem is telling you to solve. So line H passes through 3, 0, and it passes through 7, 6. So why don't I make a point at, I'll call this 3, 0, and I'll call this 7, 6. And I've got this line, why don't I change my color? That goes through these points. And then I have this other point, 2, 5. Probably be around here. What it's telling me is that absolutely there is, we talked about this before, any line, if you do a point off the line, you can do exactly one perpendicular line through the other line, right? So I know that this line must exist that goes like this. The question is, can you find some points? Can you graph it? Can you find some points that go through here? Well, what I'm going to need to do is, first I'm going to need to figure out what is the slope of my red line, right? Change in y over change in x. So I went from 6 to 0, from 7 to 3. That's 6/4, which simplifies. This is a case where it does simplify to 3/2. If that's the slope of the red line, then the slope of the blue line, if it's perpendicular, must be -2/3. And then I can just use that to follow and say, okay, how could I graph the line? Well, I need to go down 2 and over 3. So what's down 2 from 5? It's 3. What's over 3 from 2? It's 5. And I could keep going, right? I could keep going and say, all right, go down 2 over 3. That's 8, 1. And I could follow that process and sort of graph the line. So that's how we can use our understanding of parallel and perpendicular slopes to solve problems. All right. With that, we're done. Our next lesson is going to be on how do we write equations. How do we not just be able to graph stuff, not just understand slopes, but how do we take information and write an equation from scratch. That's it for this lesson.